You think Earth is floating in space because some invisible force is holding it there. Wrong. There is no up or down in space. No floor, no ceiling, no wall. You can travel in almost any direction, and you will never hit the edge of the universe. But then comes the terrifying question. If there is no ground in space, why doesn't Earth simply fly away? And why does it keep going around the sun? The answer is stranger than you think. Because Earth isn't simply floating. It has been falling around the sun for about 4.6 billion years, and it still hasn't hit it. This strange motion is connected to something called space-time curvature, and the deeper you look into it, the more unbelievable it becomes. More than 300 years ago, Isaac Newton asked a similar question. Why does an apple fall downward instead of flying upward? Newton explained it with gravity. The sun attracts Earth. Earth attracts the sun. And every object with mass attracts other objects. But Newton's theory left a deeper question unanswered. How does gravity actually work across empty space? How can the sun influence Earth from about 150 million kilometers away? For centuries, scientists struggled with this question. Then, in 1915, Albert Einstein changed our understanding of gravity forever. According to general relativity, gravity isn't simply an invisible force pulling everything downward. Mass and energy change the geometry of space-time. Imagine a stretched sheet. Place a heavy ball in the middle. The sheet bends. Now place a small marble nearby. If you give the marble enough sideways velocity, it can move around the heavy ball instead of simply rolling straight into it. This analogy isn't a perfect model of space-time, but it helps visualize the basic idea. The sun has about 333,000 times the mass of Earth. Its enormous mass affects the geometry of space-time around it. Earth moves through that curved geometry. And because Earth also has sideways velocity, it doesn't simply fall straight into the sun. Instead, it orbits. So here's the real question. If the sun's gravity is constantly pulling Earth inward, why doesn't Earth crash into the sun? The answer is speed. Earth travels around the sun at an average speed of about 29.8 kilometers per second. That's roughly 107,000 kilometers per hour. Think about that. Every second, Earth moves nearly 30 kilometers through space. The sun's gravity constantly changes the direction of Earth's motion, while Earth's velocity carries it forward. The result, Earth keeps falling toward the sun, but keeps missing it. That's an orbit. Now imagine something terrifying. What if Earth suddenly lost its orbital velocity? Without its sideways motion, Earth would no longer maintain its current orbit. The sun's gravity would pull it onto a very different trajectory. But don't worry, there is no realistic mechanism that could suddenly make Earth stop like that. Why? Because space is almost a perfect vacuum. There is no atmosphere surrounding Earth in space, no ordinary air resistance, no road friction, nothing constantly pressing the brakes. So the motion Earth inherited billions of years ago has been remarkably persistent. But then, another question appears. Where did Earth's original speed come from? To answer that, we need to go back about 4.6 billion years, before the sun existed. Before Earth existed, there was a huge cloud of gas and dust, a solar nebula. Gravity caused this cloud to collapse, and as it collapsed, its rotation became increasingly concentrated. Think about a figure skater. When a skater pulls their arms inward, their rotation speeds up. The same basic principle applies to a collapsing, rotating cloud. Eventually, the center became dense enough to form the sun, and the material left around it formed a disk. From that disk, the planets formed, including Earth. Earth inherited part of the angular momentum of that original rotating system, so nobody had to come along and push Earth into orbit. Earth was born moving. But here's where things become even more interesting. If an object around the sun had too much orbital energy, it could escape the sun's gravitational influence. It could become a wandering object, drifting through interstellar space. If it had too little, its orbit could take it much closer to the sun. But with the right conditions, a stable orbit can exist, and Earth has remained in one for billions of years. Newton illustrated this idea with one of the most famous thought experiments in physics, Newton's cannonball. Imagine a cannon sitting on top of an enormous mountain. Fire a cannonball slowly, and it falls back to Earth. Fire it faster, and it travels farther before falling. But increase the speed enough, and something strange happens. The cannonball falls toward Earth, but the curved Earth falls away beneath it. The result? The cannonball keeps falling without hitting the ground. It enters orbit, and that's the basic idea behind orbital motion. Earth is constantly accelerating toward the sun while simultaneously moving sideways. The direction of its motion keeps changing, and instead of crashing into the sun, it follows a curved orbital path. Earth's orbit isn't a perfect circle. It is slightly elliptical. Its orbital eccentricity is about 0.017. So Earth's distance from the sun changes slightly during the year, but the orbit remains remarkably stable. Now comes another strange question. If Earth is moving so incredibly fast, why can't we feel it? Think about sitting inside a smooth-moving airplane. If the plane moves at a constant velocity, you can walk around the cabin. You don't feel the plane's full speed, but if the plane suddenly accelerates or brakes, you immediately feel the change. Earth is similar. We are moving together with the planet. The atmosphere moves with us. The oceans move with us. The mountains move with us, and we move with them. Earth also rotates. At the equator, the surface moves at roughly 465 meters per second, and yet, you don't feel like you're spinning through space because everything around you is moving with you. So why doesn't Earth fall into the sun? The answer comes down to three basic ideas. First, there is no universal up or down in space. Second, the sun's mass changes the geometry of space-time around it. Third, Earth's orbital velocity keeps it moving around the sun instead of simply falling straight into it. This system has been operating for about 4.6 billion years, but it won't last forever. In roughly 5 billion years, the sun is expected to evolve into a red giant. It will expand enormously. Mercury and Venus are expected to be engulfed, and Earth's environment will become catastrophically hostile to life. Whether Earth itself is physically swallowed or not, it will no longer be a habitable world like the one we know today. But for now, we are living on a planet moving through space at nearly 30 kilometers every second around the sun, and we don't feel it, we don't hear it, we don't see it, but every second, we are moving. Every minute, every hour, every day. And perhaps the strangest part is this. We feel like we're standing still, but we aren't. We are riding a planet that is orbiting a star, that is moving through the Milky Way, while the entire galaxy travels through the expanding universe. We are not standing still. We are constantly flying through space. And maybe that's the most beautiful truth of all. Earth isn't standing on some invisible floor. There is no cosmic ground beneath our feet. We are passengers on a planet, traveling through the darkness of space, and for billions of years, this tiny blue world has carried us forward every second, without stopping, without falling, just moving. Subscribe for more mind-blowing space mysteries.